Okay, today we continue talking about the norms in Banach space. Uh, we know that the norms are kind of used to measure the distance or measure the length or magnitude of the vectors in a linear space. And the question is, there's usually more than one way to define the norm. And what are the relations between the norms? And can we use just one norm to represent any other norm? Or it really matters which norm we use? So we have seen before that for the same space, when we use different norms, we could get a different convergence result. Maybe the space is complete under one norm, but not complete under another. So in this case, we know that the norms are actually different. So our goal here is to show that in which case the norms will be equivalent. And in that case, we can use these norms interchangeably. So this is actually related to how we measure convergence. So if we have, if we know something is Cauchy under one norm, and that is also Cauchy under another norm, or it's convergent under one norm, then it is convergent under another, then we'll be able to say that one norm is stronger than the other. So this is what the definition for strong to talk about which norm is stronger than other or not. So here's the definition. We say suppose we have two norms. So I just use one, two to denote these are two different types of norms, not any other, not like the L1 norm or L2 norm. It's just the two different norms. Any norm you can, it'll be work. And let's say we have two norms in X. Then we say the second norm is stronger than the first norm. Than the first norm. If say we have a sequence that converges in one norm, or more specifically, since it's a linear space, we just need to think the case where the sequence converges to zero. So suppose this sequence converges to zero, or the norm converges to zero, implies, say, two norm converge to zero, implies that the xk also converges to zero in the first norm. Okay, so in this case, we see the second norm is stronger than the first norm. Okay, whenever the second norm, the xk under the second norm converges to zero, implies that the sequence under the first norm also converges to zero. Okay, if the second norm is stronger than the first norm, and at the same time the first norm is stronger than the second norm, then we say these two norms are equivalent. Okay, so this is what we're talking about. If these two norms are equivalent, then we can always just use one of them. We use them interchangeably, or just stick with one of them, and talk about the convergence behavior under just one of them. So we want to give a full characterization of this, not just using the definition. So there is a very easy characterization of this equation, which is given by the following proposition. It says that if x, the second norm is stronger than the first norm, if and only if there exists a constant c such that the for any vector x, the 1 norm of x is less than or equal to c times the 2 norm of x for any x in the space. Okay, so this gives a clear or more feasible way to check if one norm is stronger than the other. And the proof is pretty straightforward. So if we know this, let's show this direction first. Suppose we know there exists a constant c such that this holds. And then you can easily see that if xk, the 2 norm of xk goes to 0, this implies that the c times the xk, this will go to 0, right? And this is bigger than the x1 norm. So if this thing goes to 0, then that means this goes to 0, which means that the xk under the 1 norm goes to 0. And this is a definition. We said that if this goes to the 2 norm of xk goes to 0 next, the 1 norm of xk goes to 0 as well. Okay, so that's one. So it's pretty trivial to show one side. The other side is a little bit tricky. Suppose we know that the 2 norm is stronger than the 1 norm, and then we want to show that there exists such a c such that this one holds for any x. There exists a c such that this one holds for any x. So let's prove this by contradiction. Suppose not. If it's not, if there's no such a c, that means for any integer, we will be able to find a x. So for any integer, there exists xk in x such that the first norm of xk is bigger than k times the second norm on xk. Okay, this is the reverse way to, or opposite way of saying this. Right? If this doesn't hold, then that means for any c there exists some x such that this is greater than c times that. So let's say I just choose c to be integers. So for every k, I will have this. Okay, then what happens if I do this? Let's consider this inequality, and what it says is that when I divide k on both sides, then we'll have xk, 1 norm of xk divided by k is bigger than or equal to xk, the second norm. Okay, and then define the yk to be xk over the 1 norm of xk. So apparently the xk's cannot be 0, because if xk is 0, then both of these sides are 0. So you cannot have 0 greater than 0. That's a contradiction. So xk we chose here, they must be non-zeros. And then in this case, we can define the yk to be that, and the denominator won't be 0. Okay, if we define the yk to be this, let's see what happens is the y norm, the 1 norm of yk will be equal to the 1 norm of this. Right, just plug in yk, and apparently this is just equal to 1 because I can pull out the denominator. And inside I will have this. This is because of the homogeneity of norms, and I have that, and it's equal to 1. But on the other hand, so I have the 1 norm of each yk is equal to 1. And now let's look at the 2 norm of yk. So this is equal to the 2 norm of xk over xk 1. And similar as before, I can pull out the constant, which is denominator here, and then I have the xk 2 norm. Okay, so what happens to this is, you see I have this. So if I divide the 1 norm of xk on both sides, I will be able to have, sorry, I should have this less greater than that. Or in other words, I maybe just write it as this 1 over k greater than the 2 norm of xk and the 2 norm, 1 norm of xk, right? Just directly applying some algebra to this, I'll get that. Okay, and what this tells us is that this is less than 1 over k, as I showed here. Okay, and then what we have done is that the 1 norm of yk stays as 1, but the 2 norm of yk is smaller than 1 over k, so that means this is going to 0. So we have the 2 norm of yk goes to 0, but the 1 norm of yk stays as 1, and that's a contradiction to the condition here, because we said that the 2 norm is stronger than the 1 norm. Whenever the 2 norm goes to 0, the 1 norm should go to 0 as well, and that is a contradiction. Okay, so this is the how we show that as long as you are able to find some constant such that this is true for any x, then you can say the second norm it will be stronger than the first norm. Okay, and now you can see that if 2 norms are equivalent, then if and only if there exists some constants c that 1 norm is bounded between the same 2 norm on both sides. Okay, so that's the corollary I'm going to make. So we say the first norm and the second norm are equivalent if there exists some c1, c2 greater than 0, such that the x, maybe I still write in the first row, the c1 2 norm, 1 norm, c2 2 norm. So if this is true for any x, then we can say these 2 norms are equivalent. And that's pretty easy to see from the previous. This part tells us that this is, 2 norm is stronger than the first norm. The second norm is stronger than the first norm. And this, because C1 is positive, so it can be divided on both sides. And then we have the first norm is stronger than the second norm as well. Okay, so that's why the 2 norms are equivalent. Okay, sometimes this is written as their existing C such that the second norm is less than or equal to x less than or equal to c times the second norm. But these are just the same way of saying that. If you can relax C1, C2 to something even smaller, even larger, then you can just do this, right? So that's just a little bit tricky way to write it, but it's actually essentially the same thing. If you don't care about the exact value of C, then this will be fine. Okay, so now from this you can see that when we talk about norms, and if the norms are equivalent, then we basically can consider convergence in either of them, because they will give us the same convergence property, although not exactly the value of the distance, but it will tell us if it's actually convergent under such a norm. Okay, and in the following we'll be talking about the norms a lot, but before that, one thing we should be aware of is that under the finite dimensional case, the norms are actually all equivalent, And this can be shown by our following discussion. So one thing that we can say is, for example, if I have X as a finite dimensional B space, B star space, or Banach space, and that has the norm. If this is finite dimensional, let's say the dimension of X is n, then we know that there exists E1, En. They are bases, and they're linearly independent, and they can be used to represent any vector in X. So they are called a basis. Okay, and for any vector in X, there exists the unique vectors, so unique coefficients a1 through an, such that, let's say, such that the X is written as a1 e1 plus an e. Right, this is what we can do for a finite dimensional Banach space, or B star space even. And the question right now is, it's finite dimensional. So is there a way that we can just treat this one as Rn? Okay, it's a Banach space, but can we treat it as just Rn? And the answer is yes. If we fix the basis, let's consider a mapping between the point or vector in X and some vector in Rn, we'll be able to see some equivalency between the two. Okay, and to do this, let's consider a mapping T, and T is a mapping from the X to Rn in the following way. For any X, it will be, so the X right now is equal to a1 e1. We know that it can be written as a linear combination of the bases, and in this case, we'll map this X to A, where this A is the vector of the coefficients. Okay, let's just define our Tx to be A, which is in Rn now. Okay, so that means it maps the X, the T maps X to A. And the meaning between the two, or relation between the two, is given by this, or the meaning of X and A are given by this. So now this T is a mapping from X to R. Let's see what happens after the mapping. We can define the norm of A we can define the norm of A in this way. So let's say I define a mapping Q of A, and remember the Q of A, Q is a mapping from Rn to R, and what this mapping is, it maps every A to Q of A, but this Q of A is defined to be the this. Let me explain what we got in here. So first of all, if I define my T in this way, it would be easy to show that this T is linear, right? It's a linear mapping from X to Rn due to definition, or due to definition here. If you have X and Y, and you have two representations for X and Y, one for each, and then you can show that t of x plus y is equal to tx plus ty. And also you can see the linearity. If you have this lambda times x, it would be lambda times tx, right? That's easy to show it's linear. And also it's easy to show that the t is 1-to-1. 1-to-1 correspondence is injective and surjective. So what this t is? It's actually isomorphism, right? That means these two spaces are isomorphic to each other under this t. If it's isomorphism, then it is invertible. So we can talk about the inverse of t. We can map any vector in Rn back to x. And what that we're doing by that is for any given vector, n-dimensional vector A, we can map it to a vector x in the space x. And that vector is just written in this way, using the given basis. So the t is actually invertible, and the inverse of t maps an n-dimensional vector in Rn back to the space x. And we can, since in the space of x, we have some norm defined. See, this space of x has this norm defined. Then we can evaluate the norm of the t inverse times a. And that is what my QA is. The QA essentially is a mapping from Rn to R, and it maps any n-dimensional vector in Rn to this. This is how I define the value. So it's supposed to be a real value. So I'm going to claim several things about this Q. First of all, I would realize that this Q is linear mapping. Why is that? If I want to show this Q is a linear mapping, actually I'm going to show an even stronger result. The Q is a Lipschitz continuous function. Because right now the Q is simply just Rn to R. We know exactly what the continuity over this, right? So you can see that if you have two vectors, A and B, so the A is just A1 through AN, the B is the B1 through Bn. And now let's look at this. And by definition, the QA is just the T inverse times A. Or T inverse applied to A, and the QB is the T inverse applied to B. And by this, we know that the T inverse applied to A gives us the vector sum of A, I, E, I, as from 1 to n. Right, this is how we define the mapping from A back to the space X. So this is giving me the vector in space X using A as coefficients. And similarly, for T inverse times B applied to B, we have this. Okay, and this norm is defined, it's a norm in X. It's any norm in the space X. And you know that you can make some change. You have this AI minus BI, EI, is from 1 to n. And you know this is by triangle inequality. This tells us that this is less than or equal to sum of this times the norm of AI minus BI, EI. But again, we can use the homogeneity of norms. We can move this scalar outside, will be AI minus BI times the norm of EI. And then by the Cauchy-Schwarz inequality, I know this is just less than or equal to the sum of AI minus BI square, is from 1 to n, and then 1/2, and also sum of I from 1 to n, EI square 1/2. Okay, so now this part is the norm of A minus B. If I treat A and B as n-dimensional vector, this is just the norm, standard Euclidean norm for the vector A minus B. And this, I can call it L. I can define to be L. And this L is fixed. It doesn't change. It doesn't matter what the A and B are. This is always fixed because it only depends on the basis ES you chose. So what this tells us is that, as you can see, the distance, the norm of the distance here is less than or equal to L times this. And this means that Q is L Lipschitz, right? Because this is a So it's just that. So Q is L Lipschitz continuous. Okay, so we show that it's a continuous mapping, and we're going to show Q is homogeneous. That's pretty easy to show. So to show that it's homogeneous, we just need to notice that for any A, this by definition is the T inverse times A, right? And I know that this is nothing but just the sum of AI, EI. AI is coefficient, EI is the basis. And apparently I can divide both sides by, I can divide this by A and then multiply the norm of A. So I can just rewrite this as A times AI divided by A, EI. Assuming that A is non-zero, okay? If it's zero, then apparently it will be mapped to zero. So we get that, and then we can move out this A, and then we have the sum of AI, AEI, as from 1 to n. So essentially, I'm using this as a coefficients. So if I extract this as my vectors, as components of my vector, this is essentially just equal to A times the T inverse applied to AI or A over the norm of A. Okay, and this is just A times the, by definition, that will be just the Q of A over the norm of A. Okay, so for any vector A, we can actually define the Q of, we can see that the Q of A is essentially just equal to this. So the reason I'm doing this is now I can restrict myself to the ball or to the sphere in X only. Sorry, the sphere in Rn only. So now let S to be the unit sphere in Rn, which is all the vectors where the norm of A is equal to 1. I'm just looking at this. Now, this is the unit sphere in Rn, right? Okay, first of all, we know that the Q is a mapping from Rn to R, and it's Lipschitz continuous. I only should be continuous, but actually it's Lipschitz continuous. And now I look at the subset of Rn, which is S. I can also get the mapping. I just restrict my Q to S. But since S is a compact set, right? This is the compact set. It's bounded and closed. This S is bounded closed, so it's a compact set. So I know that when I have a continuous function defined on a compact set, I will be able to find the maximum and minimum over this set. So the Q, since S is compact, we know that Q can attain max and the mean on S. Okay, so that means there exists constants C1, C2 such that the Q of A is greater than or equal to C1, less than or equal to C2 for any A in S. Okay, so I'm only going to claim that the C1 here must be greater than or equal to 0. Sorry, must be greater than 0. It's greater than or equal to 0 is clear because the Q of A is actually non-negative. The Q maps this to a non-negative value here. So it's always greater than or equal to 0. The question is if the C1 is going to be equal to 0 or strictly greater than 0. So if C1 is equal to 0, then that means there exists some A, I call it A star, in S, such that the Q of A star is equal to 0. Right? This is where I reach the minimum value C1. But the Q of A star is equal to 0 means that this is equal to the T inverse times A star. This is equal to 0. Okay, and that just means that the T inverse A star is equal to 0 because this is the norm. So this is 0, that means the T inverse times A star equals 0. And T inverse times A star is the vector sum of A star I. This is the ith component of A star times EI. I is from 1 to n. This is equal to 0. But the EIs are bases. So this equal to 0 just implies that the AIs are all equal to 0 for any I from 1 to n. So we showed that the AI star, all the components of AI star is equal to 0. Okay, but that's a contradiction to where the A star is from. A star is from the sphere. It's from here, from this set. So the norm must be equal to 1 rather than being 0. So this is where the contradiction is. So this is the contradiction, and that means the C1 must be greater than 0. Okay, so what we showed is that this Q of A is less than or equal to C2, greater than or equal to C1, but C1 is strictly greater than 0. Okay, so this is for all the vectors A that is on the sphere. But now what if it's not on the sphere? We'll have the Q, if A is non-zero, for any vector, for any A non-zero in Rn, the A over A norm will be on the sphere. So I can substitute A by A over A norm, and I know that this is true. It's greater than or equal to C1, and also it's less than or equal to C2. But remember what we showed earlier is that the Q is homogeneous. So if I have the Q of A over A norm, it's just equal to the Q of A divided by the A norm. Okay, I just divide the norm of A on both sides, and I have this just equal to the Q of A divided by the norm of A. Okay, and this tells us that the C1 times the norm of A is less than or equal to the QA, and less than or equal to the C2 times the norm of A. Okay, and what this implies, remember that the Q of A is equal to the norm of the Q of the T, it's the norm of the T inverse applied to X, right? That's how we define the Q of A. And we show that this is this. So now recall the relation between X and A. X equals to TA. A equals to Tx. Okay, so that means X equals to T inverse times A. And that means this is just the norm of X. But on the other hand, since A equals to T of X, so I can see that this side is equal to the C2 times the norm of Tx. And this side is the C1 times the norm of Tx. Now remember that the Tx is already in Rn. So this is just a standard Euclidean norm. So what we show so far is that when we look at the norm of X, it is bounded between the C2 times the norm of Tx and the C1 norm of Tx. Remember that again, this is in an n-dimensional vector in Rn, and this is just standard Euclidean norm. Similarly, this is just a standard Euclidean norm of Tx. And this is the norm in X, in the space X. But what we have showed so far is that if we define the norm of X, you define new norm. Let's say we define a new norm, I call it a T norm on X by any X vector. The T norm of X is defined to be the Euclidean norm of Tx. And then it's easy to show that this is the norm, right? You can easily show that this is norm. It's greater than or equal to 0, and that is positive definite. It is homogeneous, and also it satisfies the common triangle inequality. It's easy to show that. And what this top line here shows that is if we define the new norm, the so-called T norm here, then we can show that the T norm is equivalent to the original norm in X, since we have this. Okay, this is what this line implies. So that means that this T norm we just defined is equivalent to any norm we actually had on X. Okay, so that means it doesn't matter what we actually define the norm for X, as long as we have a linear isomorphism T, we can use the T norm. We can define the T norm in a very simple way, just map the vector X to the space Rn and then take the standard Euclidean norm, and we'll get a norm for X. And this norm turns out to be equivalent to any norm you had on the X. Okay, so this is the very strong indication saying that this we actually can, all the n-dimensional Banach space or all the dimensional n-dimensional p-star space, they actually have the same structure or same convergence behavior, because you can always map them to Rn and you get the equivalent norm defined. So all the norms are actually defined equivalently. So this is the theorem I'm going to imply here. This is actually what we just proved. Suppose we have x1 and x2. Sorry, the first norm, second norm, be two norms on a finite dimensional B-star space X, then these two norms are equivalent. Okay, and the reason is because if you use this and it turns out to be equivalent, I would just say write it this way, it's equivalent to the T norm. And similarly, if you have another norm, it's also equivalent to the T norm. It's just that the constant C1, C2 may change, but it's still equivalent. And that's why this first norm is actually equivalent to the second norm. Okay, so the proof is pretty simple, just by following the result we proved earlier. Okay, not only that, in this case, you can imagine that if you have just a B-star space, remember the B-star space is a norm, the linear space, not necessarily complete. Only if it is complete, we call this B-star space a Banach space. But now you can see it doesn't matter what norm you're using, this X is isomorphic to the Rn. So the norm, say I have a norm, defined among X, and I know this norm is equivalent to the T norm, which I just need a mapping or linear isomorphism from X to Rn. Then we realize that this is actually equivalent to the T norm. And if it's T norm, remember that the T norm maps things into the Rn. So if you have a Cauchy sequence using this norm, it will be also a Cauchy sequence in the T norm. But the T norm is defined to be the standard Euclidean norm of vectors in Rn. So if you have a sequence, Cauchy sequence of real vectors, and you know that in Rn this is complete. So that sequence of coefficients, I would say, you just think that I have this x and each one xk. So this is my case term in the sequence, and I know that it is corresponding to, or it can be written as AI, say k is the index for the k here, AI is the coordinate, ei, and this is corresponding to a vector a1k, a_nk. Okay, and this is essentially what the txk is. Okay, so now if you have a Cauchy sequence xk, then you'll be a Cauchy sequence under this norm, but it's equivalent to that being Cauchy in this norm. But if it's in this norm, that means, remember that the t, say xk, the t norm, or I would say the xk minus xj, using the origin norm or using the t norm will be equivalent, but this is equal to the t of xk minus xj, right? This is by definition over t norm. And t applied to xk will be just the vector I got. It's just vector. And to xj is a similar thing, just a1j. It's just the coefficients I use to represent the xj. Okay, so if this is a Cauchy, that means this goes to 0 as k and j goes to infinity. And that just means this goes to 0 as k and j goes to infinity. But this is just two vectors. So that I know if you treat these vectors, if I get these vectors as a sequence, I call this, let's say I call this ak. This is just merely a vector in n-dimensional space. This is the aj, which is also a vector in n-dimensional space, and I'll realize that the ak is Cauchy in Rn. And I know that if it's Cauchy in Rn, that means ak converges something. So the ak converges to a, which is in Rn, right? And if the ak converges to a in Rn, then I know that the T inverse of ak will convert to T inverse of a. Because the T, because T is 1 to 1, right? Then this is actually the xk. This is actually what they're converging to. This is just x. So it tells us that this is actually always convergent to some point. This is a Cauchy sequence and always converge to some point, which is this x here, indicated by the limit of this vector. Okay, and what this tells us is that any Cauchy sequence in a finite dimensional Euclidean space will be convergent, and the limit is also in the space, which means that the space is complete. Okay, so our claim is that any finite dimensional B star space is a B space. It's a Banach space. So we will not have finite dimensional B star space because automatically it will become a Banach space. Okay. So this is the one interesting about the norms. When we consider finite dimensional space, it's just essentially Banach space. And also not only that, if you just have a start from a B star space, which is infinite dimensional, but now you consider a subspace. So this original B space is B star space, which is infinite dimensional. Then I have a subspace which is also B star. But if this Y has a finite dimension, if the dimension of Y is finite dimensional, then the Y is automatically B space. So although it's a subspace of the B star space, but itself will be a B Banach space. Okay, so this is some implications we can get from the equivalency of norms under the finite dimensional spaces. Okay. Now let's continue the discussion. I'm going to introduce a few new concepts. The one is called the sublinear functional. So now let's say we have a linear space X in linear space. Now I have the P is a mapping from X to R, and it satisfies the following two properties. The first one is that it is subadditive, meaning that for any x and y, the p of x is less than p of x plus y is less than or equal to the p of x plus p of y for any x and y in X. Okay, it looks a lot like the triangle inequality, but it's not. It's just think that if it's equal, then we will be able to have the linearity or similar to linearity, but they won't have less than or equal to. So it's not additive, but it's subadditive. Like we have the subadditive for measures. Okay, a second one is the positive homogeneity, or positively homogeneous, meaning that if you have any lambda which is positive, then this is equal to lambda times p of x. Okay, for any lambda greater than 0 or is in Rn plus. Okay. Okay. So this is called if we have P defined in this way, then P is called a sublinear functional. Now, I'm going to define a new one. Just don't be confused with these two. The another one is this. Again, we have a linear space, and I'll also have a P that is defined from X to R, but it satisfies three different properties. One is the same as well, but let's say just this Px is always greater than or equal to 0 for any x R. So this is the first call is called non-negative. Second is the same. It's the subadditive. It's the Px plus y. It's less than P of x plus Py. The third one is stronger than the positive homogeneity. It's called homogeneous, as we had for norms. For any lambda, it doesn't matter if it's positive or negative. This is equal to the norm, or the absolute value of x times P of x. For any x in space X and any lambda in R. Okay, this is for any x and y in the space X. Okay, so in this case, then P is called a semi-norm on X. Okay, we will be focusing on the first one, this type of sublinear functional, a lot later in this lecture. This is just to give you an idea that it's pretty similar to this so-called seminal norm. One example for this seminal norm is the TV norm we learned in analysis. TV of some function f. This is the seminal norm because we know that this is defined to be the supremum of the partitions, where the partition is I from 1 to n of f of xi minus f of xi minus 1. So what we have is that you have an interval AB, and then over this interval we can do partitions, where this is the x0 and x1, so on and so forth up to xn. So for each fixed partition, I can have this variation, so-called variation. The total variation is defined to be the supremum of these variations when this, taking the supremum with respect to the partitions. So this is a semi-norm because, as you can see, it is always greater than or equal to 0. And it satisfies the triangle inequality because TV of f plus g is easy to show this less than or equal to TV of f plus TV of g, right? And it's also easy to show that if you multiply the f by some lambda, then you can always extract the absolute norm of lambda, right? So it is called semi-normal. And what is the difference from a semi-norm and a norm? There is only one thing missing. It's this first one here. This only requires to be greater than or equal to 0. But for a norm, also need to show that it's equal to 0 if and only if x itself is equal to 0. Right? So it means it is missing the positive definite part. That's why it's called a semi-norm. It's not a norm yet. And this allows some non-zero functions or non-zero vectors to have p-value equal to 0. For example, in this case, even if f is non-zero, say f is just constant, it's any constant, the TV of f is still 0. Okay, so you have some TV of f equal to 0 when f is a non-zero constant. So this is why we call it semi-norm. But that's all we need to know for semi-norm now. We will be focusing on this sublinear functional, which has much fewer properties compared to semi-norm. Okay, so this is what we're going to focus on. Okay, so let's see a theorem telling the property of semi-norm, sublinear functional. So let P be a sublinear functional on a finite dimensional Banach space. This space is called X. Okay. By the way, we don't have finite dimensional B star space as we said earlier. And also, by the way, the functional, usually when we say functional means that it's just mapping from some arbitrary abstract space X, usually a space of functions. And it's mapping the space of functions to a real number. For any function, it is mapped to a real number. So that's why I call it a functional. Okay, so this is what P is. So P will take any x to P of x, which is a real number. But this x could be a function, since this space X is a function. It's a space of functions. Okay, a typical example is that your x is the Cm, and we know that this just contains a set of continuous functions defined on M. So for each x in this space X, this x is actually a continuous function defined on over M. So that's why when we map this x to some scalar, this P is called a functional. Okay, if P of x is greater than or equal to 0 for any x, and px equals to 0 if and only if x equals to 0. Basically means that if we know there's a sublinear functional p and that is positive definite, then there exists C1, C2, which are both positive, such that the C1x is less than or equal to the px less than or equal to the C2x. Okay, this is for all the x. This norm is actually the norm for the B space. So the B space is actually with some norm. But it doesn't matter what that norm is, as long as you have sublinear functional that is positive definite, then there exists C1, C2, such that this P can be bounded in between. Okay, and this is a lot similar to the equivalency of norms we saw earlier, but the P is not necessarily a norm. It's just a sublinear functional, okay, which satisfies this, these two. And now we're just adding that P is positive definite. Then we can still have some similar. Okay, the proof of this is very similar to the proof we had before. Again, I'm going to show that P as a least sublinear functional it is a continuous mapping, and it's actually Lipschitz continuous mapping. Okay, and here we actually need to talk about the norms. We want to show that for any x and y, I want to show that this eventually is less than or equal to L times the norm of x minus y. And this x minus y is still in the space x, and I need to take the norm of that. So that's what I want to get. Okay, so I want to show this is a Lipschitz continuous. Let's see how to do that. Apparently, this, due to the subadditivity, I know that p of x minus py, this is less than or equal to the p of x minus y. Right? You can just move the py to the right. And similarly, the py minus px is also less than or equal to px minus y. So that means the absolute value of this px minus py is less than or equal to that. It's minus y. Okay? And know that when we have a finite dimensional B space, I just think that the basis is E1 through n, and this will be just the p of the sum. For x, I use the ai as the coefficients. For y, I use the b as the coefficients. Then there will be just ai minus bi, ei, is from 1 to n. Okay, so here what I use that is that the x equals to sum of ai, ei, y is equal to sum of bi, ei. And ei is some chosen basis, any basis you can choose. Okay, I will have this. And now, again, I can use the subadditivity. The sum of this will be just less than or equal to the sum. The p of the sum is less than or equal to the sum of the p's. I will have the sum of this, ai minus bi, ei. Okay, I have that. But unfortunately, I cannot just directly pull out ai minus bi because the p is not homogeneous. It's only positive homogeneous, meaning that if I have a positive number, there, I can pull it out. Otherwise, I will not. Okay. So if it's negative number, I need to just pull out the positive part, or I need to pull out the absolute value of that. If it's 0, then I know this term will be completely 0 because I know that the p is positive definite. So if you have some constant, if this is 0, then I just know that this whole thing is 0. Okay, so without loss of generality, I can just pull out the absolute value. Let's say of ai minus bi. And then p of, I can only pull out the absolute value, so I still have the sign left inside. Right? So I only have this. But this thing is either 1 or negative 1. Or 0, doesn't matter. If it's 0, then outside ai minus bi is also 0. Okay, so it's only 1 or negative 1. But I know that doesn't matter which one is. It's either ei or either p of negative ei. Well, I know they are not negative, so I know that either one is less than or equal to the pei plus p negative ei. Right? Because they're both non-negative. Or you can choose the maximum of the p ei and p negative ei. Doesn't matter. But it will be constant. It will be bounded by something like this. So that means this whole thing is bounded by p of ei plus p of negative ei. Okay? And now I can again apply the Cauchy-Schwarz inequality. This is going to be less than or equal to the sum for n ai minus bi square 1/2 times the sum of I from 1 to n pei plus p negative ei square, then 1/2. Okay, again I'm going to call this to be L, and this is the standard norm of a minus b. But remember that this is just equal to the t norm of x minus y. Okay, but under finite dimensional space, this norm is equivalent to to any norm, right? All the norms in X are equivalent. So this is just one norm. So this t norm will be equivalent to the norm in here. So that means I can find some constant such that this is going to be less than or equal to c times x minus y standard norm. So what I have here is that p of x minus p of y is less than or equal to L times c times x minus y. And this is a constant, even independent of x and y. So that's why the p is Lipschitz continuous. So the p is Lipschitz continuous. And then after this, everything else will be similar. Everything else will be similar. We can again consider p to be define the sphere. Okay, we can consider S to be the x in the space X, such that the t norm is equal to 1. And then we can follow a similar procedure to show that this p will restore p onto this sphere, then we will get maximum minimum value, and the minimum value will be always greater than 0. And this is how we show that this px is bounded between the t norm, and the t norm is equivalent to the norm originally defined. So that's how we get this one. Okay, so that's the proof here. Okay, so now let's consider an interesting problem or application of this from the approximation theory. So in approximation theory, a very important question is that if we were given, so suppose we have applications, we do approximation theory. So suppose we are given a bunch of functions, finite many of them, phi 1, phi 2, all the way to phi n. Okay, and this is our linearly independent, assuming they are linearly independent. Okay, and let's say I have another function f. The question is, how do we represent this f using the linearly independent vector, functions above in the best way? So what do we mean by best way is we want to find a linear combination such that since all these things are from the space X, which has some norm defined over there. So we want to find the linear combination for the phi's. We call the AI, phi I. The AI is linear combination coefficients. I want to find the AIs such that this is minimized. Okay, so that's my approximation problem. It's like an optimization problem by approximating a given function f using a set of given linearly independent functions. Okay, so this can be conducted in a general sense now, right? We just have a B star space. I don't even need a B space, just B star space. B star, and I have a norm defined. So I have a B star space, which is X, and the norm. And now I can consider, say that I have a basis, or linear, sorry, it's not a basis, the linear independent vectors E1 through En in the space X. It doesn't have to be a basis, as I said, because this X could be infinite dimensional. Okay, and now given any X, I want to consider the problem of minimizing the distance between X and the linear combination of the EIs. Okay, and this is the typical optimization problem. Can we find the coefficients? The A is from A1, A2 to AN. Can we find the coefficients? And if we can find it, if this coefficient A is unique, right? That's the answer we want to. That's the question we want to answer. Okay, to show this, let's first prove that the solution must exist, and then we show that in which case it's the solution must be unique as well. So to show the existence, let's consider a mapping. I call it F. F is a mapping from Rn to R. And this F is actually defined to be the objective function right here. So the F of A is just the norm of X minus sum of AI EI. Okay, so it's just an objective function right here. I want to see if my function, right now, conceptually, this F is just a mapping from Rn to R. Is something we're pretty comfortable with. It should be just in the context of calculus. And we can first show that this F is continuous. Not just continuous, it's actually Lipschitz continuous. The reason is that we look at any vector A and B, I look at this. Then this is supposed to be the distance between that AI EI minus the X minus sum of BI EI, right? And then I know that I have, say, the U norm minus the V norm. This is less than or equal to the norm of U minus V, right? Because the triangle inequality. So this is like my U, and this is like my V. So this is essentially just less than or equal to the difference of the two, and then you can see the X cancelled, and you have just AI minus BI EI from 1 to n. This. Oh, sorry, absolute value. Okay. And then following the derivation we had earlier, this is easy to show that this is just less than or equal to L, some constant L times the distance between A and B. This L is just the sum of EI norms, square the EI norms. Okay, but anyway, it's constant. So we show that F is actually Lipschitz continuous. Okay, if it's Lipschitz continuous, then the things will be much easier. Now I just have a Lipschitz continuous function. I want to find a minimizer. What I can do is to show that the F is coercive. What does it mean by coercive? It just means that, for example, if I put this A as just this Rn just in R2. See, this Rn is in R2. So in R2, we say the function F, which defines a function from R2 to R, we call it coercive if the norm of A, or say, the value of F of A goes to infinity, positive infinity, if or as A goes to infinity. So the A is right now is a vector in two-dimensional space. So when we say it is going to infinity, means that norm of A goes to infinity. It means that the vector gets larger and larger. Okay, the magnitude of the vector gets larger and larger. Then the function value goes to positive infinity. In this case, we call it coercive. Okay, and what this tells us is that if you are trying to minimize F, then the minimizer must happen in some ball. It cannot happen outside, because when you push the value, you push the A further and further, the function value will always increase to positive infinity. So there's no way that you can get a minimizer far away, right? So the minimizer must be inside a certain ball. Maybe this ball is pretty large, but the minimizer must be inside that ball. Cannot tend to infinity. Okay? And the only thing that we need to show is why this thing is coercive. The coercive is can be easily realized by the triangle inequality for this F, because F of A is just defined to be x minus this AIEI thing, right? And this is bigger than or equal to, right triangle inequality is bigger than or equal to the norm of AIEI, I is from 1 to n, minus the absolute norm of x. Okay, and as you can see, the x is fixed. We always fix this x. And if a goes to infinity, that just means this goes to infinity. As the norm of a goes to infinity. Okay, because this is just like so this is just like the TA. Well, I'll not introduce the T anymore, but as you can see that when the norm of a goes to infinity, this one will go to infinity, and that means this is coercive, as we said. Okay, so that means this FA must the minimizer of FA must happen within certain ball. Okay, so with this we can actually say I define a P of A to be just this first part. I define to be this. Okay, now you can see that the P of A is sublinear functional because P of A plus B is definitely less than P of A plus B, right? And the P of lambda times A is equal to, in this case, actually it's homogeneous, but I just needed it to be positive homogeneous. It's equal to this, P of A. And also, it is positive definite. The P of A is greater than or equal to 0, and the P of A is equal to 0 if and only if the A is equal to 0. Okay, so I only need to be subadditive to be a sublinear, but actually with all these three, it's already a norm, right? And that can be seen from what we have here. It's actually a norm. But what we need is that right now you're on a finite dimensional space because this P of A is mapping from Rn to R. And you show that P is actually a norm, and all the norms are equivalent. So that means the P of A must be bigger than or equal to C1 times the norm of A. Because the two norms are equivalent. I just need this. I also know that it's less than or equal to C2 times A, but that doesn't matter to me now. I only need this part. And as you can see that when A goes to infinity, the P of A goes to infinity. Right? When A goes to infinity, then P of A goes to infinity. That means this part goes to infinity. And that shows that the F of A is coercive. Okay? So that means you will not be able to find a minimizer by pushing the A too far away. So the minimizer must happen within a finite ball. So let's call this ball, the radius R, it's the B of 0R. I make it closed, it doesn't matter. I know the minimizer must be within this ball for some R large enough. Well, I have a continuous function f, and I know that if I restrict myself f to be on this ball, I know that the minimizer of f must be inside this ball. But just looking at the function f itself on this ball, we know that it can reach the maximum and minimum value because this is the compact set, and my f is continuous. It's even Lipschitz continuous. So I know that the minimizer must be able to, I must be able to attain the minimizer on this ball. And this tells us that the minimizer must exist. That means I must be able to find some A such that this thing, which we call the f of A, can be minimized. So that tells us the minimizer exists.